make a lot of forecasts about synthetic data's crucial role in developing AI and analytics. And we'll be talking about, I think, hopefully by the end of this conversation, you'll have a better understanding about like why some of these buzzes are justified and where we are at the moment. And to talk about synthetic data, we need to first give a formal definition of what do we consider as synthetic data. So in this talk, my working definition is synthetic data should satisfy two requirements. One is that the first requirement is it should be algorithmically generated by a generative model, which means that the generative model needs to first be trained on some real data, and then after training, we can apply sampling or inference to get our synthetic data. And the second requirement is that the synthetic data indeed needs to capture statistical property of real data, so it can be used as a proxy or replacement or even augmentation for the real data for developing analytics and AI. There are two things that I'll explicitly not discover in this talk. The first one is data generated by expert designed simulators. For example, drug response curves simulated by PKPD models. Because the reason is that typically there are lots of experts involvement in designing these simulators, and the workflow is quite different from the standard workflow of generative modeling. Although in recent days, there are actually a lot of cross-pollination between using AI and generative modeling to aid expert design simulators. And the center has actually done a lot of amazing work in this area. But this is beyond the scope of this talk. The second aspect I will not discuss is fake data just for software testing, because those fake data are just for evaluating to make sure that the data type are correct. They don't really cover any statistical property. So now we have a good definition of synthetic data. I should remind everyone that high quality data is a very essential resource, and it can catalyze a very deep and fundamental transformation in many domains, ranging from healthcare to education to criminal justice to finance. And the ability for public sector, private sector, and research institute to share data will just catalyze a lot of change and essentially fuel the development of these fields. One particular example, this is an early example, but still is a very good representative, is the curation and the sharing of ImageNet data back in 2006. Basically, after the ImageNet, it basically triggers a whole complete transformation in computer vision and image processing. And without ImageNet, basically, we won't have the success of convolutional neural network today. However, there is still a significant gap when it comes to data. Although we have made a lot of progress in, creating the awareness of data's importance, building data infrastructure like databases, creating data normalization so that the data are having shared standards. And we also have went a long way in developing algorithms and methodology to analyze data to make it into software. But still in practice, when we are often confronted with the situation that the data I have is often not the data I need for extracting value and insight for doing my analysis. And there are multiple reasons that why the data is not good enough. The first big reason is about the relevancy of the data. Is the data fit for my purpose? Very often the data set doesn't contain all the relevant variables. It might not faithfully represent the population of interest. For example, my analysis is focusing on people with certain demographic property, but the data set doesn't actually capture that. Last but not least, all data has a shelf life, and historical data may not be future proof. It might be the phenomenon captured in historical data may already be irrelevant. And data quality is always another big issue. There could be loads of measurement error, recording error, linking error. There are lots of missing value, particularly missing not at random. And there are always bias issue with data, and pre-existing biases might find its way into our training data, and that might impact how our model performs. But even with relevant data and high quality data, there is still privacy issue. Very often, we cannot easily access or share the data because the data contains personal identifiable information or other sensitive informations. And this is all these factors contribute to the fact that the data we actually have are not good enough for the purpose. Maybe let's dive into a little bit into data sensitivity and the challenge in sharing data. A lot of countries and jurisdictions have put up strict regulation for data access for good reason. For example, GDPR and HIPAA basically prevents data holder from sharing a lot of highly granular data to the machine learning community, which might basically put a lot of constraints on what type of research and what type of question can be answered. And synthetic data actually offers a potential way to alleviate this issue. So basically, what people have found is that we could share a synthetic, proximal version of the data that behaves statistically like the real data, but doesn't contain any real example for any specific individual. And basically, the new workflow will look like that. The data holder using generative modeling technique to model their private data and build a synthetic copy of the data, which they can share with the broad community. And the resulting models and methodologies can be adopted and tested on the real private data without leaving its premise. So this is one of the first few motivating examples for adopting synthetic data in the industry. But synthetic data can also fix other many issues of real data, and actually is a unified way to address various data issues. So far we talked about privacy and sensitivity. Synthetic data is also known to create debiased data. It can help augmenting the size of the data so that we can build strong models just out of small sample sizes. It can be used for transfer learning and domain adaptation, and helps integrate data collected from different domains and regimes. And finally, synthetic data can also generate forward-looking data and future scenarios to future-proof the data, and which is especially important when we want to deploy any machine learning system into production. Talking about all the use cases of synthetic data, I think we should, now is a good time for us to have a quick, brief review of the timelines of synthetic data research and development. So back in 2020, the center and the lab basically held one of the first synthetic data event at NeurIPS conference. And at that time, we hosted a hide and seek privacy competition dedicated to synthetic data and privacy data generation. This event is jointly hosted by Vandisha Lab, Microsoft Cambridge, and Amsterdam UMC hospitals. And in that competition, the competitors are taking two roles. One are the hider roles, which tries to design a model that to generate synthetic ICU data, and the seekers or attackers aiming to re-identify the patients in the original data sets. And at that time, in 2020, the main focus of synthetic data research was still largely on private data sharing. And the key lesson that we learned from that competition is that defining the appropriate evaluation metric for synthetic data and privacy is actually a tricky problem. And since then, a lot of research has been done in that area, both by the lab and also the broader community. And now fast forward to 2021, synthetic data made into a tutorial into International Conference of Machine Learning. And in that tutorial, we focused on one vertical application area, especially in healthcare. So basically, we're exploring some real world use cases in the healthcare industry. And that turned out to be one of the first areas that synthetic data made an impact. And in 2022, we hosted a workshop on innovative use cases of synthetic data. And at that time, people have recognized that synthetic data can actually be used beyond privacy and can actually help. It has a lot of diverse use cases. For example, in generating fair data, data augmentation, et cetera, et cetera. And we have also seen a lot of more applications about synthetic data beyond healthcare, including finance, natural language processing, computer vision, and so on. And notably, the data modality for synthetic data also expands dramatically from the original tabular formatted data to time series and to images and text to and more diverse modalities. And in 2023, in the Triple AI conference, we hosted a hands-on session for the community to really build and generate synthetic data. So basically, that was an opportunity to introduce the SynCity open source package. And since then, we get a lot of great feedback and continue to improve this software package. Meanwhile, in the industry, there are actually a lot of synthetic data applications taking place in action. One example is related to biomedical imaging. So people have found that adding synthetic data of chest X-ray and histology images generated from GAN actually improves the performance of a downstream classifier. So basically, the augmented data set to a cancer detection model that is more accurate. And another success story is during COVID-19, where a team built a synthetic data generation platform so that sensitive patient data can be shared with the research community to derive insight and help combat the pandemic. So now we basically talk a lot about the different use cases of synthetic data and the goal and how synthetic data can help us to achieve to build better models and analytics. The next, we're going to introduce a little bit about more technical aspect and talk about the generative models that we actually need to build synthetic, to generate synthetic data. So first of all, we need to consider when it comes to synthetic data generation, there are actually two main pillars or desiderata. So we want to at the end of the day, we want the synthetic data to enable analytics and machine learning with some additional desirable properties, such as privacy, robustness, and fairness. And this means that we want to combine the traditional generative modeling approach with these new requirements, such as privacy. And this is because if modeling approach does not, by definition, take into account those other properties we want. Traditionally, generative modeling is all about learning the distribution and preserving the statistical characteristics of the real data. It doesn't make your data more private or more robust or fairer. But without, let's first talk about generative modeling. A generative model is a model that simulates data by estimating a potentially high-dimensional probability density function. And the estimation process can be done explicitly or implicitly, as we'll see in a minute. Generative modeling is a type of unsupervised learning where basically we want to learn the distribution of the features, of all the features. And this is in contrast with discriminative modeling or supervised learning, where the goal is to make prediction given a feature, basically to learn a decision curve or classification boundary. So formally speaking, the generative modeling problem can be viewed as follows. Let's suppose that we have a data set of real data, which may be sensitive, x1 up to xn. A generative model is trying to estimate the probability of p of x, which is the real but unknown distribution. And we build a estimate, let's call it p hat of x. And then after we build this p hat of x, we can sample synthetic data through those distributions using sampling. And of course, in designing the generative model, we wanted to handle high-dimensional data, and we want the generative model to be easy to train and easy to sample from. So those are the basic requirements for good generative models. Traditionally, generative model, the most successful generative modeling approach has been the probabilistic graphical models. You might not hear about these terms, but you might have encountered models such as mixture of Gaussian models, probability, principal component analysis, or even hidden Markov models. So all of those examples are actually falls into those probabilistic graphical models category. So probabilistic graphic models are high parameterized models. They are often linear models and admit explicit factorization using a graphical model, which is illustrated here in bottom left. So basically, the workflow of working with this type of model is, first of all, analyzing the problem and trying to build graphical models by domain expertise or through some conditional independence testing. After these type of graphical models are built, then there are standard approach to turn this into principled inference methods, such as belief propagation or Monte Carlo sampling. However, these inference methods are often intractable, and various forms of approximation will be needed. So although probabilistic graphical models has achieved a lot of success previously, especially in the 80s and 90s, they often fall short in modern applications because they make strong assumptions on the parametric form. They typically have very limited representational complexity, and the inference routines need to be designed for each modeling scenario. So for instance, let's consider the distribution of biomedical images. It's hard to find a probabilistic graph, graphical model, and come up with a factorization of the pixel distribution across different image modalities. And as another example, if we look at irregularly sampled electronic health record data, this type of high-dimensional, highly irregular and unstructured data is very hard to be summarized in a very clean model like a probabilistic graphic model. And basically, this brings us to the modern deep generative model. So deep generative models are data-driven models. They are typically trained by stochastic gradient descents, and they learn complex representations from the training data. The key idea of deep generative model is to map a noise variable, Z, into the target random variable of interest, X, through a deep neural network, F. And different deep generative models specify different loss functions in the training to learn the neural network parameters in F. And unlike neural network for classification or regression, the deep generative models are generative models that we can actually take sample from. Deep generative models broadly fall into two categories. There are implicit likelihood models and explicit likelihood models. The implicit likelihood models is a model that learns how to sample synthetic data without explicitly defining the likelihood function. Essentially, it learns by comparing the synthetic data with real data and minimizing their dissimilarity. On the other hand, there are explicit likelihood models. So basically, those models explicitly define the likelihood function and fit the distribution by performing maximum likelihood estimation. So this is more like the traditional statistical learning approach. And to see it more visually, we can see that the explicit likelihood model basically tries to try to align two parameterized log likelihood functions, whereas the implicit likelihood models essentially are doing two sample tests in some way. And the objective is to make the synthetic data undistinguishable by real data. But of course, there are further ways to categorize deep generative models. For example, in the explicit likelihood categories, there are exact likelihood methods, including fully observable models. And the notable example here is pixel RNN and other type of autoregressive models. In fact, the large language models such as GPT falls into this category. Another type of exact likelihood methods use the change of variable formulas. And the family of a notable example is normalizing flows. There are also approximate likelihood methods. These models are typically used as some way of variational inference. Examples include variational autoencoders, and more recently, the diffusion models used in computer vision all fall into that category. On the implicit likelihood model category, I guess the most well-known example is the generative adversarial network, which uses adversarial training to generate very real-looking synthetic data. And there are also other methods leveraging moment matching, for example. Another a more practical way of categorizing and introducing deep generative model is through these three axes. The first axis is the network architecture. Is it a transformer model? Is it a convolutional neural network? Is it a tabnet for tabular data? and what objective function and regularizer it is using. Is it likelihood? Is it using evidence lower bound? Is it trying to use a adversarial? And what type of training method it is employing? Is it just doing mini batch gradient descent? Is it doing contrastive learning, or even reinforcement learning? So far, we've mainly talked about generative models. Now I'm going to introduce all sorts of different requirements we can add on top of the generative model so that the synthetic data we generate actually have some desirable properties. And I will introduce those additional requirements by walking through some example generation methods and introduce them. So the first use case we want to cover today is incorporating differential privacy in generative models. So first of all, what is differential privacy? Differential privacy is a formal notion of data privacy. And basically, differential privacy is offers a mathematical framework so that we can certify or prove a certain data is private. And this is interesting because the mathematical proof actually forms a formal guarantee on the privacy that is actually universal to all sorts of attack modalities and risk models. Differential privacy is typically incorporated in synthetic data by adding noises. There are three main approaches where we can add noise. So first of all, we can add noise to the model output, or we can add noise to the model parameters, directly add noise to, for example, to the network weights, or we can add noise to the model gradients during training. So both of these three approaches will impact the design of architecture, the specification of objective function, and the training method, as we see. The first two, adding noise to model output and noise parameter, corresponds to the change in architecture because it changes the computational steps. And the last category, adding noise to the model gradients during training, apply modification to the training method by perturbing the gradients the model receives during training. In addition to differential privacy, there are also other different notions of privacy. One particular example here is called ADS-GAN. This method attempts to generate synthetic data while fulfilling GDPR privacy requirement, especially related to re-identifiability of individuals. So ADS-GAN defines a notion called epsilon identifiability, which is the probability that the distance to the closest synthetic observation is closer to the distance of the closest real observation. So basically, that captures the intuition that synthetic data shouldn't be too close to real data. And one particular advantage of ADS-GAN is that ADS-GAN actually explicitly define and control the identifiability risk so that corresponds to the legal requirements more closely. And basically here is how ADS-GAN is built on a high level. The epsilon identifiability criteria is turned into a additional auxiliary loss function called identifiability loss here. And the identifiability loss Li is combined with the primary distributional loss LD. Those two loss functions are simultaneously optimized in order to train the generator. So in this case, ADS-GAN modifies the objective function by adding a privacy-aware regularizer so that the outcome has certain characteristics in privacy. Another use case that we are going to look now is more related to transfer learning. At times we collect data from different jurisdictions and different settings, and we want to build a combined data set that we can learn from. But very often we are encountered with this issue of distribution mismatch and feature mismatch. For example, the hospital A and hospital D will have different patient distributions, and this creates a distribution shifts between locations. And feature mismatch is also apparent when the data collector collects different pieces of information. For example, hospital A creates creatinine level, but not bilirubin, while hospital B records bilirubin and not creatinine, just as an example. And how are we going to generate synthetic data that basically would allow us to merge those information, those disparate distribution together? One of the approach is called radial GAN. So in this radial GAN architecture, it tries to use multiple GAN generators to translate the data from one domain to the other domain. And it tries to solve the distribution mismatch by using the adversarial framework that ensures that the translation respects the target distribution. And it addresses the feature mismatch by introducing a latent space through which all samples are mapped. So as we can see here in radial GAN, it basically changes the architecture. Instead of having one discriminator and one generator, it actually has this star-shaped diagram with multiple generators and discriminators. It also changes the objective function and regularizer, basically adding additional loss to ensure the consistency of translation. Next, we're going to look at another very interesting aspect of synthetic data generation, and this is related to time series. Basically, we want to generate highly authentic synthetic time series data. And the goal is to try to generate data that preserves the temporal dynamics for applications, for example, in healthcare data generation. And the key challenge in time series generation is that the method needs to capture the distribution of features within each time step, as well as the temporal dependency across several time steps. And to achieve this, there's a method called time GAN, which is specifically designed for generating synthetic time series. And the architecture diagram looks like this. You can see that it incorporated several different loss functions. The unsupervised loss, which tries to help the model to learn the entire joint distribution of the time series. It incorporates a supervised loss to learn one step ahead conditionals, and it introduced a reconstruction loss to provide to regularize the latent embedding space. And it also modifies the architecture so that it can cater time series dependency relationships. So basically, time GAN is an example where the architecture is adapted based on time series, and also the objective function is adapted based on the need to model cross-time step association. Another example we want to look at is about generating fair synthetic data. Of course, like fairness in the data set will have impact on the fairness of downstream predictions. And the goal is to generate synthetic data that enables fair prediction models. So basically, in this example, we consider a particular workflow where the unfair real data is translated into a fair version of synthetic data, which is then used to train prediction models and generate predictions. The methods, one method that can generate fair synthetic data is called decaf. And for that, in order to build decaf, first of all, we need to consider the notion of fairness. What type of algorithmic fairness measure do we want to care about? And first of all, removing the protected attributes or sensitive attributes, such as ethnicity, does not guarantee the data becomes fair. And we also want to preserve data utility. And this prompts the authors of decaf to look into the so-called causal fairness. So basically, causal fairness leverages a causal perspective and use it as an intuitive guideline to achieve different notions of fairness and establish guarantees for fairness. So basically, decaf leverages the causal relationship between the different variables, and it tries to debias on this causal using this causal graph. And the debiasing step in decaf is local, as it only changes the conditional distributions that will cause a fairness issue, while it retains all the other distributions that are not relevant to fairness. So after introducing those a variety of methods and use cases, the key takeaway of this section is in order to generate synthetic data, we need to combine generative modeling with additional requirements, such as privacy and fairness. And the deep learning, deep generative models that we use to generate synthetic data can be defined or can be modified on 3 different axes: its architecture, its objective function, and the method to train these generative models. So far, we've been mostly talking about generating synthetic data, but we also need to evaluate the quality of synthetic data before we can confidently use it in any application. And in the next section, I will mainly talk about how do we actually evaluate synthetic data. So actually defining the quality of a synthetic data is highly non-trivial. Obviously, we cannot go through individual examples because we can easily generate millions of them. And training on synthetic, testing on real doesn't really tell us the full picture either. So we need a good way to define the quality of a data set. So at the moment, there are the mainstream way of approach to assessing data quality falls into 3 different categories. There are value-based approach. Basically, those approach tries to measure the value of the data set. For example, it tries to ask the question, how much additional insight or utility do we gain by adding those synthetic data to our samples? Does adding those data improve predictive accuracy? Does it uncover a key driver of a pattern? So the value-based approach are particularly relevant and powerful when we have a particular use case in mind. For example, we want to build a certain prediction model, or we want to build a certain classifier. Then we can use value-based approach to essentially evaluate the data quality. There are also so-called technical measures, mainly referring to statistical metrics and tests. Those are essentially statistical measures that tells us that the distributional distance between the real and synthetic data. And for example, some good examples include the KL divergence or the KS test. There are 3rd categories of synthetic data evaluation approach that are more theoretical grounded. So these approaches tries to establish worst case performance bounds under certain assumptions. So in practice, if you are happy to make those assumptions and you follow those assumptions in generating the data, those theoretical approaches will have a guarantee on the certain aspect of the synthetic data, such as differential privacy. But always bear in mind that those theoretical approaches are always subject to assumptions being held. The traditional metrics that we have been using, that we are all familiar with, has a lot of limitation when it comes to really giving a comprehensive evaluation of synthetic data. So in the statistic community, people tend to leverage likelihood function or statistical divergence. This has a little some problem because many of the state-of-the-art deep generative models actually do not have trackable likelihood, and we just introduced many of them, the so-called implicit likelihood methods. And when data is generated by those models, we don't even have a likelihood function for evaluation. Also, likelihood models has been shown to scale very badly with high dimensions, and defining likelihood in high dimension is not a very robust process. And last but not least, likelihood or statistical divergence basically summarize the entire distribution into a single number, which does not really distinguish different modes of failure and doesn't really give us too much insight when the data is not bad, is not good. There are also highly domain-specific scores, especially for images and audios, but those are quite narrow in their application scopes and may depend on pre-trained models and expert opinions. One of the key findings we had is that to thoroughly investigate different properties of synthetic data, we actually need multiple dimensions of evaluation. For example, the fidelity of data measures how good the synthetic sample is. So basically, is the synthetic example look like a real example? We need also to consider diversity. Basically, that is how much of the real data is covered by synthetic data. Does the synthetic data fully capture the different diversity and phenomena in the real data? And last but not least, we also care about generalization. So how often does the model just copy their training data and overfits? At the end, we need probabilistic, interpretable, and multidimensional quantities for evaluation. And this brings us back to precision and recall analysis. So here we can see in the figure A, there are two distributions, P real. PR stands for the real distribution, and PG stands for the generated synthetic distribution. And we can define the recall and precision by looking at the fraction of synthetic examples that look real, or the fraction of real samples that the generative model can synthesize, can cover, illustrated in plot B and C. And for example, in a clinical setting, we can use precision to automatically evaluate if an individual example is clinically realistic. For example, if we generate a synthetic patient with age 120 and blood pressure above 200, then that is very clinically unlikely. And we can say that this synthetic data set has low precision. We can also, so far we've talked about synthetic data evaluation on the data set level. So basically we are more or less evaluating the entire set of synthetic data or evaluating the generative model that generates the data. Another interesting aspect is we can actually apply evaluation on the sample level. And that leads to approaches like data sculpting and sanitization. Basically, we can evaluate if we can evaluate the quality of each individual data points, then we can actually remove samples that are undesirable in some way. For example, we can remove samples that are just too close with real data because they are likely to be the outcome of overfit, or we can remove samples that are not precise and doesn't look real. So far, we've already covered the full pipeline of generating synthetic data and evaluating synthetic data. So in the next section, I will mainly talk about the software SynCity, which is a practical software library that we can use to generate synthetic data. So SynCity is an open source synthetic data generation and evaluation library that implements many cutting edge algorithms in deep generative models and beyond. It covers diverse data modalities from tabular data to image to time series to survival analysis data, and enables a broad range of use cases, the ones that we have mentioned. And it contains a end-to-end pipeline for data generation and also evaluation. And the API is designed to be compatible with other libraries. The package is already available on GitHub, and you can pip install it. Basically, the goal of building SynCity is to really democratize synthetic data research and practice. For the practitioners, we want to bring the best that academia can offer so that they can have access to those fantastic algorithms. And for the researchers, SynCity can be used as a playground for experimentation, prototyping, benchmarking, and obviously for extending research impact and translational research. When we start building SynCity, we found that existing software has quite a limited scope and flexibility. Very often, when a new methodology is published, the associated code cannot be easily applied to other data modalities because it's written in a particular monolithic and not reusable way. And obviously, we cannot collect a lot of software packages to solve this problem. So what we do is to build an entire synthetic workflow in a very general way. And we designed SynCity package to achieve this. So SynCity contains three main modules. The data loader module, which is responsible for loading data and reading data from other popular Python libraries, such as pandas. The plugin module implements a variety of generative models in a very modularized and extendable way. And the metrics module that is take care of all the evaluation of synthetic data. First of all, the data loader module and SynCity's internal representation of data allows us to work with very diverse type of data. So from single data set, we can visualize it as a kind of a single spreadsheet to composite data set. And within single data sets, there are different observational patterns, whether it's static data or regular or irregular time series with mixture of different type of features and observations. For example, continuous features, integer categorical, and even censored features. And SynCity also deal with composite data sets where multiple data sets are jointly present for generation. And this could be data sets collected from different sources and domains. Data sets contain both static feature and time series feature, and data sets contains image together with annotation, etc. So this actually offers a lot of flexibility in the type of data that it can handle. In addition, SimCity also covers wide use cases. So far we've talked about privacy preservation, debiasing, augmentation, transfer, and domain adaptation. All of those are already supported in SimCity. And it can address diverse different problem settings by combining data modality and use cases. So here we have these two-way maps where one axis corresponds to the type of data modality and the other axis corresponds to the specific use case or the additional requirements. For example, we want to generate private data from static observations. Then we can choose a list of models from the corresponding problem setting, and etc. And also to mention, since SimCity is highly extendable and customizable, we have systematically built the SimCity so that it contains modularized and interoperable building blocks. So adding a new models or translating one model to another domain is actually made very easy by our architecture design. And since its release, we keep adding a growing list of supported models, including diffusion models and more recent architectures, even some of the recent methods leveraging large language models for data generation. And this is another comparison with other relevant synthetic data libraries, and you can see SimCity just captures a lot more data modalities and use cases. The evaluation framework, the evaluation module in SimCity also captures different aspects of synthetic data as we discussed just now. It measures the fidelity, the utility, the privacy, and all the theoretical aspects to serve as a more holistic benchmark framework for for thorough evaluation of the synthetic data. And since SimCity has been released online with all tutorials and documentations, and we also have built a growing community that has actually attracted many valuable contributions from the user groups and community, and will continue the development and maintenance going forward. You're very welcome to try it out sometime. Yeah. And yeah, SimCity is released in a permissive open source license allowing commercial uses, and you can use it for hosting events, and do send us feedback and contributions. Yeah, that's all about the presentation, and we can move on to the Q&A session. Thanks. Right.
Do you want me to help you pick out the questions, Zhaozhi?
Yeah.
Absolutely, I'll jump in. So the first question we have is from Aya. I do apologize, everybody, if I say anybody's name wrong, please do correct me. We've got the generated synthetic data is very dependent on the generative model and the data that it relies on. So if the training data is biased to a specific population, how will the synthetic data be able to unbias this? To represent other populations correctly, won't we need to fine-tune the generative model with additional real data sources?
Yeah, that's a great question. So yes, it is indeed in general, a phenomenon that synthetic data tends to, like the generative models tends to remember the population that it sees during training time. And but there are specific methods that can alleviate that and enables extrapolation to underrepresented domains. And actually, for example, the radial GAN that I presented is one example by, for example, translation of data points between different domains and data sources. It can actually be used to augment. And more recently, the center has done a little bit, a lot of follow-up work in this area, especially to design specific methods for better data augmentation, so that after training, we can actually population that has been underrepresented. And yeah, I encourage you to check out some of the publications from the center.
Yeah, absolutely. Thank you so much. We've got I'm not sure what time the next session is because I don't have it to hand, but I'll go with Mohammed's question here, which is more just a comment really of asking to share good references related to synthetic data. So if you have any to hand, Zhaozhi, please do pop them in the chat for us, any good references on this. I suppose would we have time to do one more, Miha, or do we need to hand over to the next session?
So we have till 4 p.m. actually till the next session. So we have, but like Zhaozhi, it all depends, I guess, on you.
Okay,
yeah,
cool.
Yeah, we can take a bit more. Yeah.
All right, fantastic. Shall I carry on doing this or shall I hand back over to you, Nabeel?
Yeah, you can hand over to me.
Go ahead.
So I guess, Zhaozhi, it was really on, like, I guess we've shared resources on synthetic data. I guess beyond that, like, we'd be curious on your opinion. Do you think also it's probably just good to play around with SynCity itself as to get like a feeler beyond even just reading?
Yeah, I think SynCity is actually a good place to start because you can see the different types of models it actually implements, and it also has several different tutorials for different use cases. So it's quite easy to get started in this area.
Okay, cool. And then there's been a few questions where it's like a bit nested. So it's really around balancing privacy of synthetic data. And I guess I'll just sort of merge the questions together. And I think it's like, how do you balance privacy with the information in synthetic data? And then it's also really around when you have privacy and addressing privacy, it's going to really impact like your downstream model performance.
Yeah. That's definitely a very valid point. Like, because in general, you do have the trade-off between privacy and utility, and this is something that just we need to like be aware of. And there are basically the recent development in this field essentially tries to, in summary, tries to introduce noise to the distribution that matters less, basically. So there's some interesting development in this area because in general, your downstream task may depend on certain conditional distributions or only on distribution of certain variables, whereas there are maybe other conditionals or other distributions that it matters less. And in principle, you could add noise or enforce noise more to those distributions that are less important. So basically using a more targeted approach to inject noise into the framework while still achieving the privacy guarantee as a whole. But in general, like the trade-off still exists. It just means where we hide those noise. Yeah.
Okay, perfect. And then I guess Rafael and Nina, I'm not forgetting your question. I'm just going to jump one ahead just because it's directly relevant to this. So Levi had a question very much related to this privacy utility trade-off. And it was really asking the question, and please feel free, Levi, to unmute yourself if I don't fully cover the question well. But it was really, how would you personally advise medical institutions to really work with this like privacy utility trade-off in practice?
Yeah, I think I think there are several aspects. So first of all, again, relates to the evaluation of synthetic data. As a data holder, it's basically a best practice to try a few different generative approaches and generate various versions of data sets and internally test it to see where the trade-off is before committing to the release. And secondly, it's also important to consider the final destination of the data set. Is the data set going to be released on the internet where the whole humanity has access to it, or the data set is released to certain research groups or certain partners? Because actually different data release scenarios has a lot of different implications about really the robustness or the security level we need. And then after making those decisions, we can actually take a more targeted approach. For example, in simulating, in identifying key privacy attacks and do some red teaming exercise even to actually identify if there's any privacy weakness. Yeah.
Yeah, and I guess Levi and Jonathan, I know you're talking a lot about this in some comments, so please feel free to unmute if you want to add something on this.
Yeah, I think a lot of this, sorry, excuse me, I'm in a busy spot, but a lot of this speaks to the importance of leadership at the level of the C-suite in healthcare organizations. And there's a fantastic article that I've just dropped in the chat from Nejum AI a few months ago about the role of the chief medical AI officer, which is probably something that I hope to eventually achieve, which is that role of clinician and someone who understands data science and AI, who can incorporate all of these systems and algorithms, but also answer these questions and provide expert analysis on, when is synthetic data accurate? When is it safe? What level of de-identifiability and unhackableness do we need? I think it's a really interesting article for people who are interested in that general discussion of clinician and scientists working together.
If I may add to that, first, let me check. Can you guys hear me?
Yes.
Yeah.
All right. Just to continue on the question I asked, you said it depends also on the destination of your synthetic data. So let's assume I am the data holder, which is what we're doing in practice. I have tested several different synthetic data generators. Then we use one of the SynCity metrics, the re-identification probability. This is where, in practice, medically trained people don't really know how to handle that, because it is just a probability. And this is what I found in practice. For example, we want to share data between just local hospitals. That's the local small scope. But how would you advise us to set that probability?
Right. Yeah, that's a good question. Basically, probability is a very abstract concept. I guess maybe you could use this probability to simulate certain scenarios to build, for example, what's the likelihood, like maybe like given a cohort of patients, how many of them will be re-identified, something like that, build a story around like that. Yeah.
All right, yes, thank you.
Okay, perfect. So now I guess we'll go back up to Raphael, if you'd like to unmute him.
Yeah, hi. You hear me? Yeah.
Yes.
Yes.
Yeah, I was just wondering about the sizes of the data set, because some generative models, such as GANs, require a large amount of data to train. How can we deal with, specifically, if we're talking about hospitals and patient data, in many cases we don't have as much data, for example, rare diseases. How can we deal with this?
Yeah, good question. So actually there are lots of methods in generating tabular or time series data can already work with thousands of samples. Some of them even might work with hundreds of samples. And this is because they use specific architecture that are carries a strong inductive bias. And it can be trained with not that many data. So this is something that we have seen that like many models are actually evaluated on smaller-ish data sets.
And I guess, Raphael, to your question. So in fact, I guess in the talk that I'm doing next, we'll actually cover that exact question. So I guess we can get back to that.
Yeah.
And the next question is from, I hope I'm pronouncing it right, Elena Anastasia. If you'd like to unmute, otherwise I could ask the question.
Hi. Yeah, sorry about I'm not sure if my internet connection is okay. Can you hear me okay?
Yes.
Yeah.
Okay. Yeah, my question was quite early on in the talk. So I was just asking about what kind of metrics could you use to assess the fairness in the data, and also whether there could be any problems with the generative models used to generate synthetic data having some kind of inherent bias. So maybe this would not allow to eliminate the bias completely.
Yeah, very good question. I think there has been like the fairness in data is actually I would say still a field that a lot more work needs to be done. So I think people have built a lot of literature when it comes to making prediction. For example, risk scoring. What does it mean by a fair risk scoring? But in terms of fairness in data, I think there still lacks a like a very principled, evaluation on fairness. Like people typically will consider, for example, representation of certain certain groups, like socioeconomic groups or ethnicity groups, and compare that distribution with the distribution of general population in a country or in an area, and see if there is divergence in the representation simply. So this is one aspect, but actually that won't paint the full picture, but because existing pre-existing biases might already manifest in other areas. For example, other conditional distribution that is harder to detect. So the DCAF method I just mentioned leverages a notion called causal fairness, and maybe that's one step towards that direction of having a more holistic and principled approach to quantify fairness in the data set. Yeah.
Thank you.
And then the next question was from Shunchin.
Hi, can you hear me well? So my question was about, I think last year's preprint about the model class. If you use a model generate content and put it back to another model training, it will cause some kind of distribution shift, especially on the tail of original data. So will you comment on that? Well, especially focusing on the medical data. Thank you.
Yeah. So actually, it really depends on the end use case and the goal. Like, so in some use cases, you specifically want to augment the tail of the distribution so that you get a more samples to capture the pattern. In other cases, you just want to generate a model that is as faithful, generate data that as faithful as possible to the real data. I guess in those two scenarios, the consideration is a little bit different. And if the goal is just to generate data that is as close as possible, then there are actually a set of evaluation metrics that you could use on the data set and also on the data point level, so that you can further do some rejection sampling if that is needed to prune unnecessary data sets away. Yeah.
Thank you.
And then Adrian, I think it's a little bit about the privacy point as well.
Hi, yeah. So I was really just wondering, in practice, how would you go about sort of explaining some of this to data protection, information protection officers in the workplace when it comes to wanting to share some of these data sets more widely? I think I'm in the process of finding that people don't necessarily understand some of these privacy metrics, and that can make it people naturally conservative when it comes to data protection. So how would you kind of advise to go about explaining to people?
Yeah, let me just rephrase the question. So basically, the question is about really how to convince the key stakeholder to adopt this type of methodology. If I'm not.
Yeah, exactly.
Yeah, I guess there is still a long way to go. Let's be honest. I think at the moment what we're trying to do is to do more case studies. So we recently just prepared a paper trying to build a synthetic version of UK Biobank and do a thorough level of evaluation. And also identify the utility of those synthetic UK Biobank cohorts in several clinical risk prediction scenarios. And so through these type of case studies and publications, thought leadership, I guess, we're getting there. And yeah, we just need the community to try more and build evidence. Yes.
Okay, yeah, that makes sense. Thank you.
And then the next question, I really feel bad that I might butcher your name, so apologies in advance. It's Siljipsevich. You would like
Hey,
to
call me Georgia. It's fine.
okay.
It's actually a quite similar question to Rafael, like previously, but maybe more in detail. Have you conducted any experiments on investigating kind of the amount of data that you need for the different models that you provide in synthicity? And I don't know, do you have any recommendations for smaller data sets?
Yeah, absolutely. So basically, we actually did a evaluation study. So basically, since City was presented as a data set and benchmark paper at NeurIPS, and we actually tested out a variety of data sets from hundreds of samples to thousands of and to hundreds of thousands of samples. And actually, to answer your questions, it depends a lot on the type of generative model you use. So particularly with small sample sets, like hundreds of samples, in my experience, the more robust model is some of the tree-based models, like adversarial random forest. I think this model is kind of currently the state of the art when it comes to small sample regime with tabular data. But as long as you have 2,000 or 3,000 of samples, you can actually have a much more diverse choice of models. A lot of deep networks start to start to perform very well in those regimes. Yeah.
Thank you.
And then the next question is from Yuanxin.
Yeah, hi. It's kind of followed the previous question, so I'm a bit curious about how do we say if my data quality is good enough to be used to generate synthetic data?
Right.
Like if I know, for example, in clinical practice, there are certain like different center variabilities or irregular follow-up or those kind of things. Thank you.
Yeah, thanks. That's a great question. Like, again, I think really depends on the use case. So one thing is to say that one application you can consider is that we want to generate synthetic data that preserves all of those characteristics, like intercenter variability or irregular follow-up, because those variability might matter for downstream analysis. Maybe we want to really analyze into the distribution or the availability of healthcare service across the country or something like that. Another application use case is to really use synthetic data to fix those issues. And in the talk I just mentioned, for example, using radioGAN to merge data from different distributions, different centers, helps eliminate those distribution shifts. And you could use other time series generation models. I mentioned TimeGAN, but actually there are more nowadays that can handle actually irregular sampled data sets and irregular follow-up. And those methods are already available in SynCity. So yeah, it depends on like what you classify as a irregularity. I think the approaches are slightly different. Yeah.
Thank you.
And then the last question we have is from Thomas.
Yeah, thank you. So I have just a question. I saw there was a paper from 2019. It's called Knockoff Qian from the Van der Schaal lab.
Right.
And I just asked myself if it's possible to use SynCity to easily generate knockoff variables for variable selection. Maybe if that's not possible right now, maybe it could be possible in the future. What do you think?
Yeah, knockoff GAN. Yeah, and I don't think it's currently available in SynCity, but essentially knockoff GAN in general, like knockoff methods are more towards variable selection. They're originally not presented as a synthetic data approach, but rather a variable selection approach. I guess that's why that's the reason we didn't include it originally. But yeah, that's a good call, and yeah, we'll revisit that. Thanks.
Okay, thank you.
And Adrian, I'm not sure if this last when you mentioned it's more comment than a question. If you do want to unmute.
Yeah, so
I don't think we can hear you very well.
is that any better? Sorry.
Yep, that's better.
Right, okay. Yeah, essentially, I've been researching quite a lot lately into this topic because it's something that I'm actively working on in UKHSA. But a number of like the most widely available data sets that I've come across have essentially been produced without using a lot of the state-of-the-art deep learning methods. So I'm thinking stuff like the Simulacrum cancer data set. There's a synth-pop package in R that's done for Scottish longitudinal studies that have been released more widely. I just wonder how much does that end up being necessary in the majority of cases to actually bypass a lot of the worries around data sharing? And do you have any sort of examples of where the deep learning methods have been used for a data set that's kind of out in the public?
Yeah, I think one example that you could take a look is MedKit. So this is a work by the students in the center, and basically we're training a simulation framework I think from, if I recall correctly, from mimic data for synthetic data purposes. And I guess like the fact that lots of synthetic data framework out there using bypasses deep learning, basically it's actually, to me, it sounds more like a limitation, because those data set often doesn't really have supports a lot of different individualized features or variables. It usually just includes a small number of variables for us to play with. And I think with deep learning method, you can actually get more variables, simulate more variables, and potentially has the opportunity to learn more interesting patterns. Yeah.
Okay, yeah, thank you. So what was the name of the
MapKit. Let me just type it.
Excellent, thank you very much.
Yeah, thanks.
Awesome, and thanks so much, Zhaozhi, for your time. I think this is a great presentation, and I think we've seen lots of engagement in the chat, so that was great.
Yeah, thanks, Nabeel. And yeah, I guess following the following section is your section, and let me just introduce Nabeel quickly. Nabeel Seedat is a PhD student in machine learning at the University of Cambridge, supervised by Professor Mihaela Vandashar. His research interests focus on data-centric AI, uncertainty quantification, synthetic data, and trustworthy machine learning. Nabeel holds a master's degree from Cornell University working on Bayesian deep learning, as well as a master's from the University of Witwatersrand, working on signal processing and machine learning for Parkinson's disease. He also holds a dual bachelor's in information engineering and biomedical engineering from the University of Witwatersrand. Before starting PhD, Nabeel has spent time working on production machine learning systems as a data scientist, focusing on computer vision at Shutterstock in the United States, and a machine learning engineer focused on natural language processing at MultiChoice, which is Africa's largest multimedia company. So without further ado, Nabeel, please start. Thanks.
Thanks so much, Zhaozhi. You know, when you can. Am I sharing the
We
right?
can see that.
Is this the right screen or is it the PowerPoint one?
It's the PowerPoint one, is that right?
Ah, yes. Okay. Oh, wait, it's like the one you do see my slides changing.
Yes.
Okay, perfect. Okay, yeah, so hi, afternoon, everyone. I think you've seen a lot of me the last few days. So yes, I'm Nabeel. So I'll be talking about data-centric AI. So just a little overview of this little tutorial that we'll cover today. I'll give a brief introduction to data-centric AI, be going through a few like data-centric considerations, this idea of we've been building something like a systematic tool for data-centric AI. Then really, this topic area is pretty broad, so we couldn't cover everything probably in a full hour. So I've chosen to cover a topic area called data characterization, which are systematic machine learning methods to curate data sets, and then looking at applications of data characterization. So where can you use it, whether you work on tabular data, whether you work on images, whether you work on text. Then ending off with data-centric AI and this intersection with the world of large language models, and then just some future outlook based on like what we've been seeing as like trends in the field. So as just a little disclaimer, this talk is by no means exhaustive. It's not really a review of a lot of what's going on in data-centric AI. We've seen quite an explosion, especially since I started my PhD a good like 3 years ago, where this was a very niche topic. We've seen tracks at big machine learning conferences. We've seen a data-centric AI workshop at every machine learning conference, and we've seen a dedicated data-centric AI journal crop up over the last year to year and a half. So this field is really like blown up quite a lot. So I think it's just very hard to cover everything at the moment. So it's really going to be biased by my own experience and expertise. And obviously, I'm going to be missing some topics and publications. So just as an introduction, really to give people an idea of this paradigm of data-centric AI versus model-centric, and what do we really mean by this. But before getting into that, it's really this idea that everyone at the moment talks about that machine learning applications are actually everywhere. People talk about machine learning being in the clinic, machine learning being in finance, self-driving, e-commerce, criminal justice, manufacturing, a whole load of places that you see news articles showing machine learning actually being used. However, the reality is just getting machine learning to work in the real world is just fundamentally really, really hard. And what you can see on the slide here is just numerous examples where very big companies have even struggled putting machine learning into real world settings. For example, Google's medical AI, where they trained it on data from well-curated data sets in the lab, and when they took it out to the field in different countries, those algorithms really struggled and performance was different. Amazon systems for recruitment using machine learning had issues of bias. We've had many issues around algorithms having sexist and racist undertones, etc. And I think really the big finding from all of this, where we've seen getting machine learning just to work reliably in real world settings being really hard, the main issue has really been around data itself and issues around what data models are really being trained on and how does that really match up with the real world. And it's because the fact that real world data itself really already has errors. We know machine learning data sets, which are these well-curated benchmarks, people have done studies on them that they have many, many errors in data sets even that you might think are quite perfect, like ImageNet. People have done studies on them, and you've seen 10 to 15% labeling errors on data sets like ImageNet. And then once you even go to more real world data sets away from the curated data sets that we find in machine learning, we see that healthcare records and patient records might have misinformation and false information. So those are, of course, going to affect machine learning systems. And of course, we see this in like many other applications. And I guess one thing just to mention, I'm pretty normally a bit bad with the chat. So if somebody does have a question as they're going, even just feel free to interrupt without putting the hand up and stuff. I'm a bit bad with these type of things, so just feel free to jump in. And then beyond actually just errors, we know real world data itself also has inherent biases. We're collecting historical data. And of course, if we have collecting real world data, we're going to start building systems on such data. We then start asking the question, will biased clinical decision-making that went into these data sets start creeping into our machine learning systems? Unequal access to resources and allocation actually being in data sets, then perpetuating into our machine learning systems. And then the fact that also many of our electronic data sets that we actually have when we think of electronic health records really contain sampling biases, depending on the countries that we really have access to. Not all of the places across the world really have access to electronic levels of data sets. So this is going to lead to less representative data sets used to train machine learning models. And we can see this like loop where biases start perpetuating. So it's really this issue that we really need to start thinking, and the machine learning community has thankfully at least started thinking a lot more about this, of how do we start thinking and rationalizing about what data we even put into a machine learning model in the first place? What impact is that going to have? And potentially, can we use machine learning to try address some of these issues? Because clearly these are very, very hard challenges for humans themselves to even address. And that's where data-centric AI is really this like major opportunity, where very similar, I think, to what Zhaozhi showed in his presentation. Again, we've got many of these articles talking about bad data causing machine learning tools to be really bad, with Gartner showing like 85% of machine learning systems really will fail because of erroneous outcomes due to biases in data. And when you put like some financial projection number on it, clearly there's a lot of money involved as well to solving this bad data problem. So it's really like a big issue. However, the fact is, machine learning, when we think of being done in an academic setting, when we think of the major conferences, really is done on sanitized data. So we have benchmark data sets, and I know I did talk about benchmark data sets themselves being somewhat erroneous and having issues in them. At least they're a bit better than real world data sets. But the fact is they are still at least somewhat to a degree sanitized, and it's not really real world. And the question is, all of these algorithms that we show that perform really well on these performance benchmarks, the question is, how well do they translate when we then take them to real world data sets, knowing there's this significant mismatch in the data? And I think I spent a lot of time showing all of these huge problems in data. However, unfortunately, it's still very much just something, a very undervalued problem. I think everyone would find this paper from Google a few years back quite interesting, of everyone wants to do the model work, not the data work. And what they really show in this paper is that the issues around data really early on in your machine learning pipeline, both right at the collection and labeling stage, and really when you like analyze it and prepare it for models, is really the area that's really neglected in the machine learning community. And when people are building machine learning models, with everyone wanting to get to the really fun part of building the model and training it and evaluating it and showing it we have state-of-the-art performance. However, if we don't solve what happens upstream, what this shows is it leads to something they've referred to in the paper called a data cascade, where errors that do permeate right in the beginning are just going to affect everything downstream, irrespective of you having a really good model and training it really well. You're still going to have many of these issues that are there. So I'd encourage everyone to take a look at this paper if you've never seen it before. And the thing is then, we've heard this point data is the new oil, and we've contended this word that if there are all of these challenges in data that I've shown you in these last few slides, the thing is we're starting to now need refineries for this oil if we really want this little adage to be somewhat true. So right now, the overall approach is we just have raw data. We think it's like a great gold mine, and we can just throw it into our latest and greatest machine learning model. Especially these days, you can just chuck it into an LLM and hope for the best, and you'll get really good machine learning insights, and the problem will be solved. You'll make really good classification. You have good performance. You'll make good forecasts on time series. And the reality is, though, it kind of misses this data refinery here in the middle. And it's really this idea of broadly the data-centric AI community is starting to say, how can we build tools to really be at this intersection right in the middle of this word data refinery, really putting a data-centric lens on and saying, how can we put data somewhat of a forefront, build systematic tools around it, and then take our latest and greatest machine learning models, which are predictive, and then throw it on the data. And so the current approach to machine learning, and you'll see a lot of this, I guess, in the summer school, and more generally, the more classical approach to machine learning is this term model-centric AI. And it's really that you have some sort of training data set, and the assumption that's there is data is some sort of fixed asset. We go to Kaggle, we get a data set, we get an image repository of medical x-rays. Within a company, we can go query a SQL database. But really, the fundamental notion is that data is fixed. It's some sort of fixed asset. Once we've pulled our training data, that's the data set. And really where our focus should be is model iteration. So how do we build new models? How do we build new architectures, loss functions, optimizers, etc.? And of course, this is like very fundamental, important research. Like I'm not contending this at all. I think huge amounts of algorithmic advancements are still like important, and it's important for people to really work on these things. But in the data-centric AI community, there's been really this contention. It should not be the only focus when we think of building machine learning models. There really needs to be an additional focus and quite a significant shift in focus really to data iteration itself. So really building systematic tooling, so machine learning tooling to doing data acquisition in a more principled way, to cleaning data, to auditing it, and based on our last presentation from Zhaozhi, so generation of data as well. And once we have these systematic tools in place where we can now iterate on our data, it's not really this fixed asset. We can then take it to our latest advancements in model architectures, whether it's a neural network, boosting a transformer, etc. And so given this here, just to anchor everyone in the presentation, just to give a little bit of a definition of what do I mean by data-centric AI. So it's really this idea of methods and tools to systematically characterize, evaluate, and generate the underlying data, both used to train machine learning models as well as evaluate them. So there are actually two paths to this, or at least instantiating this definition that we've really seen broadly from the community. So this idea of like characterizing data, evaluating, and generating, it's how can we use data-centric insights for different things? So the first is, well, if we can understand our data through systematic methods, we can curate our data sets better. And this could be the model performs better. We can remove some erroneous samples. And the fact is, if we can curate a good data set, rather than maybe throwing 1 million samples at a machine learning model, if we can curate only the high quality samples that are actually going to lead to good model performance, this is also good from a fast computation perspective. And you'll see some examples later in the presentation. And this is this idea of data sculpting and data pruning. And we've seen a lot of this beyond even the supervised learning. So we've seen a huge amount of work being done in the supervised learning, but a lot of this has really started to creep into the large language model arena as well, where how can you select the best examples to train the large language model on, rather than just throwing the whole of the internet at it. And then the second is really this idea of how can we, if we have insights about our data itself, can we use that to actually guide our model's improvement during training? And it's really this idea of curriculum learning ideas where by understanding the data, we can then train models on very specific curriculums. For example, training on models on certain samples first and certain samples later on in training, and how do you introduce them at different rates through the training process. In this talk here, given the time limitation, I'll really only be covering the first bit, but there's a lot of good resources and research to which I'll give links to in the end on the second bit. So really, I'll be focusing really on this idea of data curation. And then just before getting into that, just for everyone's purpose, and I think this is a nice reference slide, it's really what are some common data-centric tasks. So you might say, like, what is a data-centric task beyond just data curation, as I mentioned? So the first is, as I mentioned, data characterization, really detecting erroneous or noisy examples in machine learning data sets. I'll be showing a lot about this. There's machine learning literature on things like outlier detection. So once you've trained a machine learning model and then you've deployed it, can you identify incongruous examples in your data set? And I'm giving some references that you'll see to packages that are already doing some of this very well. So PyOD is definitely a great package that really captures quite a lot of different methods from across the literature. So that's really great. Missing data imputation, so completing data sets. So especially this is a huge issue in healthcare where you do have missingness often of samples, and something like hyperimpute from CCM is something I definitely recommend on that. Then there's synthetic data generation and data augmentation, so increasing data samples, and I think Zhaozhi has shown a lot on Centric, so I don't need to talk a lot about that. Then there's active learning, so selecting informative data to actually label. So given an unlabeled data set, which should you actually send to a domain expert to actually label? And then semi and self-supervised learning, so making use of unlabeled data. I know this somewhat does become slightly homogeneous with other research fields. You might say semi and self-supervised learning have actually existed for quite some time, and active learning as well. It's many of these fields have also started adopting these ideas of like data-centric AI. We've seen works in semi-supervised learning and self-supervised learning, not even just doing it on all of the data, but really doing data curation first when doing semi-supervised learning, and doing data curation first before learning the representation for self-supervised. So really saying we shouldn't be learning our representations on all of the data. What data is the best to give us and learn good representations? So that's why it started being a little bit pulled into this area as well. And really, though, when we started looking at a lot of this here, where you can see there's many data-centric tasks. And really what we've noticed from this here is a lot of these fields have really developed really independently from each other, and they're very disparate, separate research directions, where people are working on active learning, and there's a very thriving active learning research field. There's thriving imputation fields, thriving data characterization fields, thriving synthetic data fields. And all of them have really been separate fields of one another. And what this does is, it's great from a research perspective, but when we think of practical implementations, it really ignores the machine learning pipeline as a whole, where how do all these different pieces really interact with one another if you were to actually use them in a pipeline, because you might be using many of these things in conjunction with one another. And can data-centric thinking really help when we start like threading these things together, when we start building out an actual machine learning pipeline? And that gets me on to my next bit of the talk. So if anyone does have any questions at this moment, feel free to stop me before I move on. Okay, so the next section is really on this idea of data-centric considerations. So it's a systematic tool which we've called DC Check, and really it's starting to address this point that I've talked about in the last slide, which is really saying actually machine learning systems need to start, or at least practitioners really need to start thinking of how these things actually integrate with each other, these separate research threads, and how can we put them together and really think of them more holistically. And it's really this fact that data-centric AI is important, but really hard to engage with because we don't have this like standardized process. We don't have guides for these necessary considerations for how these different things interact with each other. What should you be using at different phases? And also, what are suggested tooling? Like, what are best practices that we're starting to see emerge across the broader literature? And also, what are really opportunities where these are actually just gaping holes where people should be doing research, and we hope this spurs additional research. So this is something now about a year and a half back, which we've introduced is something called DC Check, which is a data-centric AI checklist. And really it's this idea is we wanted to help both industry practitioners and researchers really as a guide for development of reliable machine learning systems more broadly. So when you think of data-centric considerations, the first thing that probably pops into your mind is this is at the data stage when I'm actually building my data set. And our contention in this work is actually the considerations around your data shouldn't only be at the data stage. So not just around doing like proactive data selection, which you can see in the figure, pre-processing, quality evaluation, synthetic data, but you should also be thinking about how does data affect actually your model training? Can it actually, can the data set that you have inform your model selection? Do you need a specific inductive bias based on your data set? Can your data be informed by your usage requirements? If I plan to use my model across different domains, I might need to have training processes that are informed by my data to do domain adaptation, to do domain adversarial training, etc. Could you actually do training which is actually subgroup robust, some things like group DRO, because you know actually that from your data perspective, subgroups are actually really, really fundamentally important, for example, in a healthcare perspective, and you care about the fact that actually you want your model to perform really well across different subgroups. And this can inform the fact that you actually want to train your model with something like group distribution robust optimization that you do to have good performance across different subgroups. And it's really this idea of how data can inform how you actually train your model. And if you know your data that you're going to have is going to be potentially noisy, you might do data robust, like data noise robust training methods. And then finally, really on the testing and deployment side, we really wanted to get this point that the data itself also doesn't just simply fall out of the picture at that point. Really, how should you go about thinking, assessing your data sets? So of course, right now, everyone's just got this validation set. You run your whole model on this validation set. You pop out one evaluation number on average, and you say the model is doing really well or it's not doing really well. And our contention there is you really need to start thinking, like people need to start thinking more deeply about how do we assess different subgroups, like people should be assessing different subgroups in the same way like the medical domain really are very stringent about really stratifying performance numbers. How do we do evaluation when we have very small data sets for evaluation in small subgroups? Can we use tools to augment those data sets to actually get an idea where your model might fail? And then at the deployment time, can we actually really start like methods should be put in place that do significant data monitoring to see distribution shifts and how this can inform model updates of your next generation of models. So it was really to get this idea across of how can we think about data holistically across the data pipeline beyond just in the data phase itself. And you can see more at that link there. And both in this paper, it's getting across this point, but really what we then try to do is provide tools for each of these sections. So like what is the latest and greatest from amongst the whole machine learning community to address these? And especially then where are actually some research gaps that based on these areas, actually there aren't tools that really satisfactorily address some of these things, and people should start working on them. And we hope this will like motivate that. So it's really to get to be really an actionable and standardized process. So it's really a checklist when somebody is designing a machine learning system to even just put something in the back of their mind, like, have you thought about some of these things? And for both the practitioner and researcher to really give this idea of like transparency, accountability of what you've actually done when you've developed your system. So yes, you can see a lot more here. And this is kind of what I discussed of the different like areas of data training, testing, and deployment, and why we really need all of these different considerations and not just data at the data stage itself. If there are any questions at this point, please feel free to jump in. Okay, cool. So then I guess I'll jump on to data characterization. So data characterization is really looking at systematic methods of like, how do we actually even curate data sets? So we know there's many challenges that you might face even in a supervised learning data set. So we might have examples of mislabeling images of a cat, which is just erroneously labeled as a car or a dog, depending, maybe it was on like Mechanical Turk. We might have mismeasurement on an e-commerce system. Somebody might have clicked like the incorrect rating on some review. They wanted to give it a 5-star. They've written very nice things about the product, but by mistake, they've clicked the button one. The person doesn't even worry about changing it. So you've got mismeasurement that you have in your data. You have noisy data as well. So this is like measurement devices in a hospital where you have issues around like devices go out of calibration. So you have noise in your actual data or injected by humans themselves. And then there's error propagation, especially if we're collecting data, which is like propagated from one system to another, and we've collected it only downstream. We might have data corruption itself. So we might sometimes have like measurement artifacts. So example, blur in images, causing ambiguity if we want to do something like a classification task. And then in like the healthcare setting, we even have challenges of just like patient heterogeneity of healthcare outcomes, that there's just the fundamental heterogeneity of biology, which leads to challenges in data, which can affect machine learning models. And then finally, the biggest is really like underrepresentation, especially in a healthcare setting, that we often have data sets where there are specific subgroups which are just fundamentally underrepresented, and models are going to perform better, worse on them compared to the larger majorities. And how do we actually address this? And then finally, I want to give 2 examples, which are just maybe a bit more visual. So imagine we've got a large scale image corpora of pictures of people. Imagine we have an image which looks like this here. We can clearly see it's like a bit blurry. There's been some measurement artifacts. Really, how do we go about, if we have millions of images, how do we actually go about finding these images in the first place to actually remove them, because they actually might be harming our model training? Or if we've got, for example, a large scale sentiment analysis data set where we've got somebody saying really amazing things about whatever this movie is, and they've given it a negative rating. So this is clearly a labeling error. If we've got millions and millions of these as well, how do we go about autonomously actually finding these? This is really hard for human beings. We don't want humans to have to go comb through all of these data sets to really like finally do auditing, because it's just really time consuming. And so what really data characterization as a broader research area tries to do is auditing and curating of data sets, and really saying that doing this auditing and curating of data sets at scale is very hard and very time consuming. And the question is that, well, not all data is equal to one another. So can we build systematic tools where we can assign scores to individual samples within the data set? So whether you've got a tabular data set, a time series, an image, a piece of text, this should be somewhat modality agnostic. That can we build general purpose machine learning methods that can effectively score different samples based on things that we actually care about, different value functions that we really care about. So one obvious value function is how much do these individual samples contribute to model performance? So how much gain am I really getting for having these samples, and having methods that can assign such scores? And it's really to get to this essence of which samples in a data set are actually learnable for a machine learning model, which samples are actually important to learn on, which samples are fundamentally ambiguous, which samples are hard, which samples are actually just like mislabeled. So really trying to understand at like a more fundamental and principled level, can we start building methods to pinpoint these learnable and important samples, these ambiguous samples, or these very hard to learn? And these are, when I refer to hard to learn, it's not samples that you probably should be learning just because they were actually not like captured, like underrepresented. In the literature, and this is obviously just bad naming from the literature, when hard to learn is often just listed in the literature, it's often just that the data sample is just fundamentally incorrect, like the wrong label has actually just been assigned on it. So no matter what you do, if you were to make a prediction, you probably aren't going to learn very well on it, because everything around it just looks and is labeled very different. And I just want to highlight this area or research stream of data characterization is somewhat orthogonal to the area of data valuation. And for that, I'd recommend taking a look at something called Open Data Val, which is quite a nice benchmark also from last year, which looked at the data valuation side of the literature. They're somewhat orthogonal, but share a lot of like similarities as well. So when trying to assess these samples for, I guess, like learnability and actually curating a data set, we've really got two different paradigms. So the first is, what are model-centric methods trying to do about the situation? So model-centric methods say, well, my data is a problem. So how can I change my model simply to be robust to the situation? So can I build a robust model with something like domain adaptation? Can I use noise robust losses or other robust layers? Can I use loss functions from another network? So methods like co-teaching and MentorNet. Can I modify my loss directly, or can I do like importance reweighting of individual samples to kind of make my model more robust, knowing the fact that my data is potentially imperfect? And then from the data-centric perspective, the community has started thinking of, let's think of this from a slightly different paradigm. So instead of having a robust model, could we have a robust data set to start with? So this idea of improving the data set, selecting those samples which are important and learnable for a model, and then flagging those which are like hard/mislabeled, getting humans to actually look at them, and then reintegrating them. But we obviously need to first find issues in the data set, and then we can learn either with or without the issues by providing this quote unquote cleaned data for training. And for this, we really need new machine learning methods to actually solve the right-hand side of this problem. So there's really been a wide variety of data characterization methods developed in the literature, and you can see it's really over the last 2 to 3 years at like really maximum. You can see it from all the citations. And it's really that across these different data characterization methods, I've tried to bucket it based on the class of methods. So really, what are the methods really trying to fundamentally do? So we've got the first that you can see in red. It's something called margin-based. So really assessing the margin of a classifier. So between the like your highest logit and your second highest logit, what is that like difference being your margin? There's uncertainty-based methods, some of which I've worked on. Then you've got gradient-based methods, which evaluate gradients through model training. Some look at the loss of a classifier itself to try characterize samples, and then some look at forgetting. And I'll get into a few of these in more detail as we go on. But then I wanted to break it down and say, let's try and look at where's really been the application of these methods. So of course, these methods are never developed in some sort of a vacuum. They often have actually been developed for very specific applications, and what has their role been? So you can see here that actually a huge focus has really been to audit large-scale image data sets very specifically, and it kind of makes sense because there's a huge demand, for example, to audit these very, very large-scale image corpora, your image nets, etc. And there has been a small amount of methods for like text and like tabular EHR. So clearly there's definitely opportunity to really say, do some of these methods actually work very well across different modalities, or do they actually really work for a specific modality, and then there's room for actually research to actually build on in these other modalities to take into account like the nuances of the actual data. And then additionally, the task itself. So given the data itself, like what was the actual data that people have actually used to audit, like what were the data sets and models that are being trained? You can see most people have been looking at supervised classification problems. We last year developed the first approach on data characterization for regression data sets called triage. But more broadly, the literature is really focused on, I've got a classification problem. I've got this very big data set. Can I audit samples in the data set? And then can I prune the data set because my model will train a lot faster? I'll achieve the same level of performance, or that I might even get better performance, has really been like the overarching goal. And then we see that, of course, you might say, okay, so there's different classes of methods targeting different modalities, and for the most part, targeting classification. But what's the thing that really binds all these methods together? It's really this common notion of training dynamics. And I'll get onto it on the next slide. And it's really this idea of training dynamics, which is like the harmonizing factor between these different methods. And then I'll be breaking down to how do we go from this common notion of training dynamics to these different classes of like margin-based, uncertainty-based, gradient, loss, and forgetting-based. So really training dynamics, what do they do? So for those unfamiliar, training dynamics really look and study the behavior of samples through the training process of like model training. So where it really came from was the more theoretical machine learning literature, where people started studying how do neural networks itself learn. Like people tried to study in the learning theory literature, how do neural networks actually learn? And the finding, of course, was that neural networks learn samples differently through training. Some samples are learned early during the training process. Some samples are forgotten during the training process. Some samples are learned late in the training process. And what this data characterization or data-centric literature has really picked up on this point of, well, if the neural network is actually learning samples at different times, so some samples are learned early, some samples are learned late, some samples are forgotten, is this not actually reflecting something about the property of that very data samples themselves? And really it came to the idea then that shouldn't we actually be studying the behavior of these samples in a way to actually characterize which of these samples are doing what? So you can see an example on the screen of like a training dynamic. So this is basically just a set of training. So say a model being trained for like 20 epochs. You can see in green, these are quote unquote what are being called easy samples. So these are samples that are just learned very quickly through the training process and never forgotten at all. There's some samples which you can see in orange, and maybe the shading is not that perfect, but hopefully you can see my cursor moving, that there's a lot of variance in their true probabilities. So this is, the model is almost correctly predicting well. Then at the next epoch, there's an update and the model forgets it, and there's a lot of variance there. So there's clearly a lot of ambiguity in the actual data samples themselves. And then finally, you've got this set of hard examples. And once again, I'm just gonna flag this when I mean hard. These are, like you might say, well, we should be training on hard samples. I'm just flagging these again. These are, for example, mislabeled samples. This is the reason why an actual model like just never gets these samples right through training at all, just because there's something fundamentally wrong with these samples with respect to the other samples in the data set. That's why the model actually just never learns them through training. You can carry on training for however long you want. You could throw a bigger, add more layers on it. The model just won't memorize it even in the first place. And then what the data characterization literature is doing is saying, well, we've got this training dynamic that you can see on the screen. Can we build different principal scoring functions? So this is like this function S, which is going to be applied onto this training dynamic. And that's really the fundamental difference of all those different classes. It's how all of these different scoring functions have really been formalized and what these different scoring functions actually capture. So I'll be going through a few like representative works from that table. I won't go through everything because I guess it gets a bit much, but obviously we'll be sharing the slides so you can go look up some of those papers in a bit more detail, but I'll be trying to cover a little bit from each class. So the first is really this paper from Place et al. At NeurIPS 2020, which is really the margin-based class of methods, where they try to identify mislabeled data using something called their scoring function called the area under the margin ranking. And it's really basically looking at the scoring function S of X over your training epochs, like little t equals 1 to t. And basically the area under the margin is really the assigned logit, like minus the largest other logit that you have there. And their hypothesis from the paper is that low margin scores, so those with like small margins between your assigned logit and your largest other, are actually samples which are mislabeled. So you can see this clip from their paper on the screen, where very large margin is like the correct dog label, and this very, very small margin that you see here is actually this image of a bird being labeled as a dog, and the scoring function being able to capture it. Then we've had methods called deep learning on a data diet, so finding important examples in training from Wall et al. Of NeurIPS of 2021. And they had actually two different scoring functions, both of which are kind of show to be approximates of one another. So the first was the Grant score, so like the norm of the gradient through training. And they showed that this is actually somewhat equal to the much cheaper to compute EL2N score, which is the norm of just your error vector. So your predicted output versus your Y. And just in case this wasn't 100% clear, we do have the Y because we're auditing the training data set. So during training, we actually have like the ground truth. y. And their hypothesis was that these examples, which have very high norms of your error vector or have very high gradient norms, these samples can actually are like these very noisy samples, and we can actually prune them out, and you can get similar performance to if you just didn't use all of the samples actually. Or if you don't want to prune them, these are examples, at least from the perspective when you think of applying this to a healthcare setting, you don't want to lose data, to actually then send it back to a domain expert for further review. And then the next method is data IQ from our group, which was characterizing heterogeneous subgroups in tabular data sets. The title of this paper, unfortunately, could never ever be changed. It does do a lot more than tabular data. It actually does do images and text as well, but the title always stuck as tabular data, but this is very applicable to images and text as well. And it really takes an uncertainty estimation approach to this. So it computes a two-dimensional scoring function, or S of x. So the first is a scoring function trying to compute the inherent aleatoric uncertainty in the data. So this is your inherent inability to predict with certainty linked to the data. So this is not the uncertainty that if I just threw more samples at it, I'd get better. This is actually the inherent uncertainty in the actual data sample itself and the confidence. And it then gets projected onto this two-dimensional map where we've got average aleatoric uncertainty and average confidence. And we're able then to disambiguate some samples which are easy for a model to learn, some samples which are ambiguous for a model to learn, and some samples which are hard for a model to learn. So these are like these mislabeled samples. And the hypothesis was there from our paper was that ambiguous samples, especially, and I'll show some examples later, are these very uncertain types of samples within your data set, that there really isn't only a binary of easy and hard, that there's actually this middle gray area of uncertain samples, rather than just saying there's only a binary and then you've got these very hard mislabeled samples which can be pruned out. Dataset cartography from the natural language processing literature from EMNLP took something similar, and they did it on epistemic uncertainty. So it was just a little change on the method there. Then the next one, and I know this is just like a whole bunch of methods, so I'll just breeze through them a bit quickly, and people can spend more time going through these on the slides, but I think it's just to give a bit of a flavor of what these scoring functions are, is variance of gradients. So here what they do is they estimate difficulty of examples using the variance of the gradient through model training. And of course, there the hypothesis is that a gradient will just, if it varies a lot through training, it's probably these challenging examples. You can see like low variance apples are these pretty red ones that you always expect from these pictures. And then these really challenging pictures of apples actually are the ones where the gradients actually vary a lot and the model really struggles to pick it up during training. And I think what it really gets to is all of these methods are doing this autonomously rather than a human having to comb through the data set. And then finally, and I believe this is the last one from the set of scoring function-based methods, it's really small loss, and they try to do sample selection via, like from a noisy label perspective, it's saying those samples with large losses are actually potentially just going to be mislabeled. And those with a loss over the course of training are actually probably quite fine. And this might obviously be quite intuitive, but they showed particularly quite interesting, insightful results. I then want to flag one last method, which is not actually training dynamics based at all. And it's a paper from Northcutt et al. From the Journal of AI Research. And what they do is they don't take the perspective of training dynamics, but it's still this idea of auditing a data set. So their idea is that given you have some trained machine learning model theta that you can see, and you have some potentially noisy data set, how can you estimate some noise transition matrix, which you can see in this picture there? And the idea is that if you pass your noisy data through your predictive model, you're going to get some noisy output like y hat, which is like your noisy predicted probabilities. And then they try estimate something called what they call the confident joint. And how do they do this? Well, they simply kind of count. Well, they say that anytime, say, the real image was labeled, like the noisy image was labeled dog, the model had predicted dog, will count all the instances of that. Every time the noisy image was labeled dog, then the model predicted fox, will count those. And what you can do is you can then just normalize the rows to effectively get a probability, where the off diagonals effectively give you an estimate of what fraction of the data set is actually mislabeled. So their intuition in the paper is that 10% of dog images would be in reality fox images. And the only purpose of just showing this here is just showing that there are other paradigms beyond training dynamics. And then I really wanted to just flag this paper, which I talked about before, as like our method, which is called triage, which is really to characterize regression data sets, because we really understood this problem is very important in a healthcare setting. Regression problems are also quite significant when you think of like length of stay prediction and many biomarker type of predictions. So this is just a different method based on conformal prediction to use training dynamics, but actually build a different principal scoring function using conformal predictive distributions. So I've shown you a lot of like methods at this moment, and you might say, okay, you've shown me all of these methods, like there's so many methods out there. Like, what do these things actually do in the first place? So we want to show some applications of what can you actually do with data characterization and why should you actually care. So I'll show you some examples of what it would be to use a data characterization method to audit a text-based data set, to audit an image data set, and to audit a tabular data set. Like, what would you actually get out? So to audit a text-based data set, so for example, groups which are easy examples, which you can see on the screen, this is kind of obvious. So this is like a movie review. We see that the first negative review with the label has a lot of like red and very mean things to say about this movie. And so it's obviously quite a correct review, and positive, which is in green, says a lot of nice things there. So it's kind of reasonable why a model would find this easy to learn on. Ambiguous examples are actually where it gets quite interesting, is that actually when a data characterization method, something like data IQ would run, we'd be able to actually pick up examples where there's linguistic ambiguity in the text. So you can see here that part of the review is quite positive, part of the review is quite negative, and a data characterization method would be able to pull this out for human audit. And then finally, hard examples, which you can see on the screen, are just like these mislabeled examples where the review is actually negative in the text, got a positive review, or it's really positive and got a negative review. So you'd be able to automatically like pull it out of your text with a data characterization method. And then moving on to image data. So for example, easy examples, we look at the Celeb A data set. So you see all these very crystal clear images. So it's kind of reasonable why you'd want to train your machine learning model on these very easy, perfect images. Ambiguous is where things actually get quite interesting, particularly from the responsible AI perspective. So a data characterization method flagging examples. So this is not to say you should never train models on these. This is really for flagging purposes and for you to really understand your data set. It really found that images of females with shorter hair are considered ambiguous to a machine learning model. And of course, this is like some degree of bias that we probably don't want reflected in our machine learning models themselves. And it's really because these sorts of images which were tagged as females and having shorter hair are just significantly underrepresented. And what a tool like this would allow you to do is flag this issue in the data set, such that somebody can actually go rectify it and we don't go perpetuate these biases. So just thinking of a utility perspective. Additionally, it would be able to flag things like blurry images or images which are like obscured, at least, but flagging these to somebody to actually really take a decision without having to go audit all millions of images themselves. And then finally, hard images like the text are just mislabeled or incorrect ground truth. And then getting onto the healthcare case of, say, auditing a tabular data set. So tabular data, what we really thought about is it really different from these unstructured modalities like your text, like your images? Is there something really different about tabular data? And I'll show you one very interesting thing. So this is an example of a machine learning model trained on a prostate cancer data set, really trying to predict prostate cancer mortality based on a set of patient covariates. So say we've trained a machine learning model, we then run a data characterization method during this in the loop process, and we say, okay, look here, what are actually the easy to learn examples in my clinical data set? We can see that patients who are less severe, they have very low PSA scores, they have very low stages of prostate cancer. It's natural why the model is going to predict they're going to survive, and likewise for severe patients with high PSA scores, high stages, that they're going to have the mortality outcome. What then is interesting, though, in the ambiguous case, is that actually we find these are actually very similar patients, but patients who have very different outcomes when we think of the actual label that they had. And on consultation with the clinical experts, what we actually found is of course, these are patients where we just simply we probably just haven't captured all of the covariates necessary to disambiguate these patients, given that they have this very different outcome. But from the perspective of what you would have collected, these are actually the perfect candidates to go run more diagnostic tests or collect more features on. We wouldn't need to collect more features on everybody. It would just be this subset who it's really hard to disambiguate between them unless we collect more features, which is quite an interesting application. And then finally, hard examples are those like patients with like a heterogeneous outcome that we actually might want to flag to a clinician to actually have a look at. And then how much you use this beyond just like flagging a data set, one could, in theory, sculpt the data set for more reliable models that deploy. When you deploy them, we show examples where if you were to train a model in, for example, in the United States and then take it to the UK, or train it in the UK and take it to the US, and you were to actually sculpt the data set to remove some of these examples, which are actually just going to harm model training, the model actually generalizes better when you take it across the distributions. I'll just finish this last bit on how to apply it before I move on to the next section, and I'll stop for questions there. So say you'd actually want to take this to your own data, like how would you actually go about doing this? So we've put together a package called Dataagnosis together with Rob and Mihaela. And really the idea is to bring all of these methods, so these 12 that I've shown you, or 13 that I've shown you, really under this like unified interface and API with like an extendable plugin style interface. So as more methods come out in the literature, they can really be extended. And you can find it on GitHub under Dataagnosis. But really to just give you an idea of how we've tried to make it easy and make this like process really approachable to people to get a start, so you don't have to go dig about in like a research code, and it's really like nicely wrapped up in the same way like Centric is. So you'd be able to just like get your data set. So this is just an example of getting your data set. You'd be able to then have a Dataagnosis data handler where you'd pass in like X and Y with some like batch size for your model training. And then you get your machine learning model that you really care about for your task, whether it's an MLP, whether it's a CNN, whether it's a transformer. That's really up to you. And you need to just obviously set your parameters for your model, like your learning rates, like whether you want cross entropy, what's your optimizer, etc. That's all up to the practitioner. And then you get your hardness characterization method. So this, for example, say you want to get variance of the gradients, you pass in your model and your criteria, and then you call fit along with your data handler. So what this does is it trains the model, captures the training dynamics, and then applies all of the different criteria. And then at the end, you can get your scores to say, these are the easy examples, these are the ambiguous examples, these are the hard examples. And then somebody can then go take a decision on what they actually want to do with these samples with respect to model training. If there are any questions at this point, let me know. Otherwise, I can take all the questions at the end if that's easier, before I just finish the last section. Okay, so I guess I'll finish up then with the last section. So a lot of what I've talked about up to this point has really been supervised learning. How can we apply all of these data-centric issues in the supervised sense? Of course, this is still like going to be a huge area of supervised learning. I don't think it's going away anywhere soon, but really we do need to obviously acknowledge this big elephant in the room of large language models and what have they really done to the space. So the first is I'll be talking a little bit about data-centric AI for large language models, and then flipping the script a little bit and saying, what can large language models contribute as an example towards the data-centric AI literature? So, but first on how is data-centric AI and this data-centric thinking really affecting the development of large language models? So we've seen that training of large language models actually have just been really fundamentally about the data itself. Everybody knows the architectures, everybody knows how to train a large language model. And the really big thing about language models is really the data that's being the key differentiating factor. And a paper definitely from last year that I definitely recommend having a read is from Gunasekar et al., which is textbooks are all you need, where they show that a very high quality curated data set is what you really need to train an LLM, and it can achieve very similar performance than if you just threw huge amounts of data at it. And both OpenAI and open source developers like the TAI, which developed Falcon, have also talked about that their biggest issues or big issues when training language models has been like errors in the data during training and they spend extensive amounts of time filtering things like the pile and Common Crawl, often using humans. But we've started seeing a lot more literature, which has started building on this work from supervised learning and bringing it into LLM training to actually curate the data sets, to actually train the LLM, and really making that process of curating the LLM training corpus more systematic and principled. And then basically, I really want to say, could LLM, like, if you're not going to be an LLM developer, which most people aren't going to be training their own LLMs in the near future anyway, where actually, what could an LLM contribute to unlocking a data-centric AI problem that's probably been some degree unsolved? And this actually builds on from Zhaozhi's talk, where there were questions about synthetic data and very ultra-low data regimes. So how do you do synthetic data when healthcare, maybe you have only 50 samples, maybe you have 100 samples. It's not the same types of settings where we have thousands and thousands of samples, where we can train GANs, where we can train VAEs, and everything will be great. So unfortunately, like machine learning, we know presupposes vast access to lots of data. And as I mentioned, clinical settings, so healthcare, and this is specific settings where it's just hard to get patients. And additionally, from our thinking, we were like, well, there's only certain bits of the world actually that even have electronic health records in the first place. There's many bits of the world that don't even have an electronic health record, and hence you can't do machine learning in the first place there. But while you could collect small amounts of samples, less than 100 samples in undigitized form, and digitize those, such that you can bring machine learning to those patient populations as well. And in the pharmaceutical industry, also very sample constrained, often in clinical trials. And of course, it's going to be suboptimal for ML. And how can we solve this? And really, it's this idea of how do you make augmentation really work? So synthetic data has widely been used to augment these types of very small data sets. However, current tabular generative models will really struggle in these very low data regimes. So whether using a GAN, a VAE, a flow, you're either going to get significant overfitting to these examples. Additionally, what you really have with a current tabular generative model, if you only have 50 samples, those samples can only, when you generate synthetic data, you can only generate within those the manifold of the samples that you've really been given. And the problem with that is you just don't have diversity in what you're actually generating. So you're really only going to be reflecting the diversity of those 50 samples that you actually have in the first place. And what we asked ourselves is, can large language models help to generate diverse tabular data? And the answer was yes, but of course, language models are not the silver bullet in the first place. So language models might get diverse data, but well, the language model could also hallucinate things when it's creating a tabular data set. It might make up features that are actually medically implausible, or examples where the feature-to-feature interactions simply don't match, or the feature-to-label relationships are just simply off, because you're asking it to generate very diverse data, but there's no guarantees of what pops out on the other side. So the question is, how do we balance the risks of LLM-generated data? And it's really how to ensure high-quality LLM-generated, or more generally, synthetic data that reflects the real data. And this is something which we've called curated LLM. So really, the idea of this work was, so imagine you've got a data set in a clinical setting of maybe you've got 20 patients, 40 patients, 100 patients. We could prompt an LLM to generate a black box LLM to generate a huge amount of synthetic data that's quite diverse. We then have a curation function. And why it's quite interesting, it builds on ideas of learning dynamics that I've shown in the earlier slides, really showing this interaction or intersection between these areas and like these ideas of learning dynamics to produce a curated data set, which we can then train a downstream model on. And really what the learning dynamics really tries to do is it actually tries to assess how does the synthetic data learning dynamics match up with the learning dynamics of the real data set itself. So if we assume the real data set is perfect and represents what we actually care about, and we've curated it really well, we know it has certain properties or behaviors that that data will actually exhibit through training. And what we do is then we run the synthetic data set through a model which has been trained on the real data set, and we see how do the trajectories of the synthetic data set align with the real data set, and use those to throw away the samples that don't align with the behavioral properties of the real data. And you can we can have more questions on this if there is, or you could read the paper. But I really wanted to highlight is what is the actual outcome. So LLMs plus curation really help a lot. So you can see here, so we baselined against various traditional generative models like your GANs, your VAEs, your tabular diffusions, your SMOTs, your normalizing flows. And we benchmarked both on public data sets, but as well as private medical data sets that would have been impossible for the LLM to have seen in the first place. So really to see that and make sure that the LLM hadn't just memorized the data set already, like it would have been impossible for it to have had access to it. So we actually see that what's very interesting is that GPT-4 plus curation, even when it's trained on 20 and 40 samples, has downstream performance almost to the level of an oracle, which is thousands of samples. So we held out a set of 2 to sometimes 5,000 samples, depending on the actual data set that we had. We trained the oracle model on that to see what is the upper bound of performance that we can get. We then said we have 20 or 40 synthetic, 40 real samples. We're going to generate a much bigger synthetic data set from that. And then we're going to see how close do we get to this upper bound that we had if we had a lot of samples, and how much gain do we have if we just train on this very tiny data set. And we actually see significant boosts because of the LLM itself. And beyond just like the GPT series of models, we also looked at like Mistral and Llama, and we see very similar performance with the curation mechanism. But you might say, well, this is kind of just like magic. Like, why does this even work in the first place? It just seems crazy that the LLM can just like make up data. So we really tried to understand what is the LLM fundamentally doing. And the first insight was the LLM actually has a capability to extrapolate to regions of the data manifold where we don't even give it training data in the first place. So what you can see from these plots here, so where like the light blue is the actual oracle data set, so this very large data set that we've held out. Little black dots are the actual training data that we've actually had, like when we had 20 samples, when we had 40, when we had 100, when we had 200. And then we compare a VAE to GPT-4. And what we see is that that the TVAE in green is obviously naturally confined to the data manifold of where we have the black dots, or where we have training data. But actually, the LLM, which are these red dots, are able to actually extrapolate to bits of the manifold, obviously after curation, where this is actually reflective of real data, which is actually quite an interesting insight of the extrapolative capabilities of a language model, which you can kind of see over there and there. What we did also find of like, where are the significant performance gains really happening? And it's really, we found amongst these very small subgroups of people. So patients like in our sample set, which we just had very few samples, is where we'd get the biggest downstream performance gains when we take it to large scale big test data. So like testing on the population. And then most importantly, it's actually the finding like what really makes this really tick. It's really that the curation mechanism aligns your distribution of your real and synthetic data much better. So your Y given X relationship becomes much better aligned of those samples that you curate and keep versus those samples that you throw away, where this learning dynamic behavior isn't reflective of the learning dynamic behavior of the real data. So it's really trying to understand what's happening, and it's really this alignment of what we actually keep versus what we throw away. And then you might say, finally, okay, well, this works. So if I'm in a real healthcare setting, so I'm in a hospital, I really want to know and flag poor generation a priori. Like, I want to know my generation is poor. I don't want to go train my model, test it on people, find out it's really bad, and then be like, oh man, my data was actually kind of bad. Can we actually have a proxy right at the beginning to know that actually the data was actually pretty poor? And what was actually quite interesting is that there's quite a strong negative relationship between the amount of samples that actually get discarded and your downstream AUC on a test set. So if you end up having to throw away huge amounts of data, you should somewhat be a bit skeptical of what you have, because it's likely that the model's just not going to perform really well downstream. If you're having to throw away huge amounts of data, it means something's definitely gone wrong in the LLM. And especially the big reason for this is because LLMs are black boxes, unlike a GAN and a VAE where you can like monitor the training process and you can see what happens to a loss, an LLM, you're literally just putting serialized data in and getting data out, who knows what happened in the middle. So you kind of need some degree of oversight to actually understand what has actually happened with your data. And then finally, I'd just like to end off, and then we can jump into some Q&A on where do we see the future of data-centric AI, given this little bit of a run through that I have here. So I think it's just a really exciting research area to be in at this moment. I think there's been a lot of growing importance, as I mentioned quite earlier. And I think that there's 4 main areas which I think have really growing, and we've seen the community really starting to tap into these a lot more. So the first is just really this idea of right now in the data-centric AI community, there's really been, how can we build methods which are model agnostic? So irrespective of the task, irrespective of the model, let's do that. And the question is that all we need? Should we be tailoring things a bit better? The second is, we do need to be going a bit more beyond supervised data, so to graph data, to RL, to LLMs, because of course these issues of data really fall into these areas as well. And then the last 2 is really going beyond this like very hard delineation. So in this talk here, you would have seen I've made a very hard delineation between data-centric and model-centric, but really, I do actually believe there really should be this synergy between data and model, and like having your insights on the data, connecting to the model, and really having this like iterative loop between them. And I think that's actually where this really should be going. And then really finally to like multimodality, like all of the work has really been done single modality. So how do you audit an image, text, and tabular data set independently? But what does this auditing actually look like when you've got a multimodal paired data set? So like text and a radiology image, or a time series and some nurse notes, for example. Like how do you actually do data characterization there? So thank you for that. And I guess I'll jump into questions, and I'll leave it on the slide here. Just these are some like interesting resources from broadly across different areas, the data-centric AI community. Thanks. So I guess I don't know if Andreas or Mia is there, but I guess I can take the questions myself. Let me just see if I get to the start. So I think Jake.
You have a question from Yusuke, from Kano, if he can answer, or maybe already answered.
I think Mia Jake is at least the first one I see.
Kano, if you want to ask the question, please.
Hi, thank you very much for your presentation. My question is more about the concept of data-centric AI rather than a particular method. So we still handle the corrupted or low quality data after deployment. So how do we deal with that data? Is it the scope of data-centric AI? I just wondered if the robustness of the model could be decreased if the model is trained on the very curated data.
I guess I do think I'll answer the question in 2 parts. So I think there has been a fair bit of research, especially on the deployment time, trying to understand how different, and I think especially the data is at deployment time compared to actually just at what you've actually trained the model at. I think a lot of that the outlier kind of literature would probably fit very well. There's low quality corrupted, and I guess that would be just maybe a systematic deviation from your training set. If I recall, in DC Check, we did put a few more papers in research areas that did cover that, but they're just slipping my mind at this moment. So I know in the paper we did cover those. I think it's been a bit of a while. And then I guess just to your second question on robustness of the model being degraded if it's trained on very well curated data. So I know that I 100% agree that there is always this worry about it. And I think it's a little bit down to the wording we use when we think of it sounds like we're creating very sanitized data sets. And I think it's just more we're saying, okay, well, there's samples in the data set that might be just like fundamentally incorrect, that the model shouldn't be training, like due to like human annotation error or like human measurement error. So we shouldn't even be training the model on it because it actually harms the model learning, and like downstream performance is actually worse. And I think what some papers have especially shown, especially in the computer vision literature, that they can still achieve the same levels of performance as those models that train on like millions of samples, but just by targeting those like 5 to 10% where like some human on like Mechanical Turk maybe is like mislabeled it, that they can get faster performance, remove those, but still like achieve the same performance as like the much more expensive to train model. But I think it's always something that before you like throw data away, especially I think in the healthcare setting, it should be like these data characterization tools, I think, should have like a human in the loop just to like audit and say, well, do we actually want to train on these or not, rather than like fully throwing them away in like an automated way.
Okay, let's see. Anissa, all right, I don't know if you already answered to this question. But what about samples which are hard to learn, may take longer to learn, but are labeled correctly? Will pruning them decrease the robustness of the model?
I think that's a great question. So I think the one thing especially, and I think it's just the wording of like, I think like I've always had worries about the word hard in the literature. I think it creates a lot of confusion, and it's really been these samples which are hard are even those that like people have shown where you train them for 100 epochs, train for 500 epochs, train for 1,000 epochs. The model just won't even learn it late in training. And that these are the samples we're calling like hard. So for example, if you like to give like a very crude example, if you've got like 10 images of dogs in your training data set, and one of the dogs is labeled cat, it's always never going to get the label cat right. It will always try predict it as dog, and that'll affect the model training. So the model will like never get the true label right just because of everything else that's around it. If that answers your question.
Okay. Then Yeman, I'm sorry again for sharing your names. Sorry. If you want to ask your question. Okay, how can we apply the training? Okay, excellent. He's okay, please.
Hi, thank you for the interesting presentation. My question, actually, I have two questions. The first one is, how can we apply these training dynamics-based data characterization methods during inference? The second one is about this training dynamics-based data characterization methods and class imbalance when we have huge imbalance within our data. Then maybe we can have samples with correct label, but the model can misclassify them. Will it be confusing the model like with the hard labels?
I think those are actually two very good questions. I think the first one is definitely the one I think I've grappled a fair bit with, and I don't think there's maybe like a super great solution. So I guess, most of these methods have been like to characterize a training data set where you actually have like your label. And then I guess the problem is that like your inference time, or like I guess testing time, you should also assume you don't have the label. Is that the best that's really been done? And I don't think it's satisfactory, but like I guess it's something. It's been to like take the training set, run data characterization, like get your groups of samples, like say your easy, ambiguous, and hard. You then like embed those, and then at testing time or inference time, you get samples and embed them as well into the same space, and then see, do they embed with the hard samples? Do they embed with easy samples? Or do they embed with the ambiguous samples? But I don't think it's by any means like a perfect approach. But I think it's one of those where there's definitely more research to be done on that, especially on the inference time. And then I guess the second question, I think that's definitely fair. So I guess like even if it's very, very class imbalanced, right? So say like you've got this like class mismatch. So if you are going to be training, say, your machine learning model for maybe like you're going to overtrain it, you could like, for example, overfit it. The model probably will at least pick those up. So if you train for enough epochs, the model will at least learn it. I guess the only difference is when we're thinking of hard examples, these are just like fundamentally mislabeled. So it's this word of like, I guess, unlearnable samples rather than like, I just think it's a weird naming that creates a bit of like confusion around this. But I would say in a class imbalance setting, it's probably still good, at least I think, then to have human oversight, given that one never knows, to your point.
Thank you.
Okay, Julia, do you want to ask your question? Thank you.
Thank you. Nabeel, that's excellent talk. Thank you so much. Yeah, I've learned a lot of things. So I was just wondering about the training dynamics hypothesis. Do you think it will hold for the textual examples? Have you probably already tried that if there is synthetic text which is generated?
I actually haven't. I think that'd be a really cool research. But like my intuition is, I guess if you've got like a text data set, which I don't know, like maybe you've got like a classification task, that at least some of the properties, like you're hoping that your generated text captures the same like linguistic behaviors, because then the model will have the same learning behaviors. Like if it's like completely crazy text, I guess the learning dynamics on the front, because what it is you train on the test set, on the training set, you'd freeze the model and then you'd like run your synthetic samples through this like frozen model. So if the synthetic examples really went crazy and were very different, you'd really capture it in like the training dynamic or like that learning dynamic behavior being quite different. So my assumption is it should be good, especially because I guess like the data characterization has been used to, I guess, sculpt text-based data in the supervised setting.
But thank you so much, Nabeel. But I guess there will be little margin for fine-grained hallucination detection, right? So
Yeah.
if it is hallucinated a bit, then it will be more complicated. Okay.
Yeah,
Right.
because I guess in like a tabular data set, it's easier to
Yeah.
kind of pick those out because it's like a much bigger hallucination across columns rather than like tiny
Yeah.
things which just like linguistically fine.
Mm-hmm. All right. Thank you so much, Nabeel. I think there are really a lot of questions. Excellent
Julia.
talk. Thank you.
Okay, thank you, Julia. Adrian.
Hi, yeah. Thanks for a great talk. I was wondering specifically about the point at which you were producing the synthetic data. Do you consider the characteristics in the data that you discard as well during pruning? I'm just wondering, is there a danger of disproportionately removing certain subgroups because they're harder to classify?
I think especially like where it gets to like the medical case, like I know, I guess in like images, people are quite easy, like more easily just throw things away. I know in especially the medical case, like especially that hard subgroup where like, you know, I showed where it's like the patient could just be mislabeled, but they could have also just had like this heterogeneous outcome because patients who are super healthy sometimes do actually just have the mortality outcome by a random chance. And like 100% agree with you. Like I think that just, especially in healthcare, there just has to be the oversight before you prune it. Like I'd be super worried to automatically prune anything without at least like consulting with somebody who's a domain expert.
Right, okay, yeah, that makes sense. Thank you.
Jake, do you want to ask your question?
Yeah, absolutely. Can you hear me?
Yes.
Fantastic. Thank you so much for a fantastic talk, Nabeel. Great way to end off a second fantastic day. So thank you. So my question is regarding whether the few different things that you've worked on actually come together at all. Like, is the curated LLM approach included somewhere in this DC check framework, or is that on hold really until some more LLM approaches are developed and then that's added to it?
So at the moment, I think DC check is a lot like confined, I guess, to like just the supervised stuff. I think it's like kind of DC check came out and then curated LLM came out.
Yeah, of course.
After the fact, and like I know we did like word it as yes, we'll be updating it, and I think we probably do need to update it because things keep changing way too quickly.
Yeah, of course. I mean, there could even be a framework specific for LLMs as well, couldn't there? Which is a really interesting thought.
No, 100% agree.
Okay, and I think this one is the last one. If somebody else wants to raise the hand, and okay, Zhaozhi.
Hi, thanks again for the great talk. My question is about like the differences between the strategies that you presented for data-centric approaches and the selection strategies in active learning. How similar are they, and are they complementary? Because some of the strategies that you've shown, like for example, the probability-based, it's also a common strategy in active learning. And for example, other strategies like entropy-based or margin sampling, are they also used in data-centric strategies? Or maybe you can elaborate on that.
Yeah, like I think I 100% agree. I think there's like a huge amount of like at least synergy between those two areas in terms of like the strategies based, and I think especially around the uncertainty estimation based stuff. I think there's a lot of like synergy that could be in like the active learning. I guess maybe where the only difference is, I think fundamentally, is the task itself, where like say data set like these data characterization or that like data valuation literature that I didn't talk about but I referred to is saying like, okay, I've got a collected data set. I can't maybe go collect any more. And then how can I assess them to actually decide what to keep or not to keep? And then I guess the active learning is I start out with like a small amount of data, and then I've got this big unlabeled pool. What do I go and label? And in fact, why I think there's definitely a lot of synergy there. So we've recently done like a work on semi-supervised learning, which is like very related to active learning, where you've got this big pool of unlabeled data, but instead of, I guess, asking like the human being to label it, like the system does the labeling, and then we assess how the label goes through the different like loops of semi-supervised learning. So I think there's definitely like a lot of synergy there.
Perfect. Thank you very much.
This was the last question. So if anybody would like to raise the hand, or if not, I can thank Nabeel for everything, for the amazing presentation and today, because she was the host of many talks. So he will join you even when I open the meeting rooms, because he will be also the mentor for today's session. So thank you, Nabeel. You are amazing.